Yeah, so I get asked a lot about how you say my first name, so much so that actually on my website there's a little WAV file that you can click and listen to that if you want to, but for all intents and purposes, I just go by Benko. Yeah, so thanks so much for having me here today. I'm super excited to be here and to talk to you guys about the stuff that I do. So I come from land up in Puget Sound area, Microsoft Research. It's in Redmond, and I've been there for about 6 years. Prior to that, I did a lot of augmented reality work. I spent a good portion of my PhD years wearing a head-worn display, walking around like a zombie, and now since I joined Microsoft, I've been dealing with some of the similar concepts, but dealing them through slightly different means, as Michael said, mostly projectors and cameras. But fundamentally, I'm interested in how do you extend the interaction vocabulary? How do you extend the interaction bandwidth to communicate between humans and computers? In a sense, try to look at not so much replacing the interesting and good ways that we already have with our input devices, but how do you extend that with new sensing capabilities, new sensing modalities, to make the interaction with computers less digital in a form and more analog to the real world, but analog in nature, not so much on and off as much as kind of gestural and expressive, the way that we have the dexterity in our hands and in our bodies to interact with the physical world. We've been trying to look at the same methods to do that and to apply that to the digital content. Now, the first project that I did when joining Microsoft, this is just a little preview there, is just creating a funky little, I would say a toy, where we started with, at that point, this was before the iPhone and before all these different things, the tabletops were all the rage, so we did a spherical surface just to make a point that we can turn any shape into an interactive display. So that's fun. After that, I did some even more ludicrous things like churning a dome into a fully interactive dome. So this is kind of like your instant planetarium. You have a blow-up dome, you have a little projector in the middle, and not only can you do that, but literally by just putting your hand in front of the projector and moving things around in midair, you're literally navigating through the stars and exploring all the stuff. Needless to say, this is a really popular demo. We actually showed it at Kai, we showed it at a bunch of different places. Kids love it. You have multiple people kind of enjoying the space, and it's really easy and interactive. All you really do is like reach in front of the projector and move the thing around, but with this little pinching gesture. All right. Also, as part of it, I've built a bunch of cardboard domes. So if any of you need some instructions for Burning Man for how to build some of these geodesic domes, all you need is paper clips and cardboard, and you get some really nice rigid structures like this, as long as you're willing to spend some time cutting this precisely. So anyway, it's a lot of fun. The black parts are where the two cardboards join. We wanted to have a really dim dome inside, so we actually put a piece of black paper, just folded it over the fold, and put paper clips on top of it to hold it so that there's no light leakage. It's not actually structural. No, that's just a folded piece of black paper. Yeah, good question. The other thing, throughout this whole talk, I really like audience participation, so if you guys have any questions, feel free to raise them right up front. We don't really need to wait until the end of the talk here. If you're shy, you can come and talk to me afterwards as well. I understand there's both types of people. As Michael said, as part of the great thing about working at Microsoft Research, or pretty much in any industrial research lab, is that there is a conduit for your ideas and for your thinking to make it into products and to have other people use it. So I've worked as part of Microsoft Research and as part of product teams. I worked on several different things, including the old Surface model, the Microsoft Touch mouse, which stemmed directly from our WIST paper called Mouse 2.0. I spent a year with the product team making that. That's actually a first device, and pretty much the only device right now that allows you to have a curved capacitive sensing device. So device is sensitive to both gripping and gesturing, and the same surface is used for both. In many other cases, by the industrial design of the device, you design it so that where you're holding the device is not actually triggering any input. In this particular device, where you're holding it, how you're holding it, it's all part of a sensitive surface, and we need to do some smart inferencing based on are your touches currently being used for gripping, or are they being used for interaction, which makes it challenging but also quite interesting, because you can use the full dexterity of your hand to interact. Also, the same team that did the Microsoft Touch mouse ended up doing the touch cover, the Surface covers, so a lot of different cross-pollination and a lot of different venues for moving this kind of research into products. But what I'm going to talk to you today is this idea of how do you turn any surface in your environment into an interactive surface, which is something that I've been thinking about a lot over the last 5-6 years. And I'd like to start with this idea of showing you the devices of today. Now, I belong to a certain company, and you can pick any company you want and substitute the images here. But in general, what you're faced with today is this idea that you're interacting, and most of it is flat, rectilinear, 2D screens. Most of the content that you're interacting with is also that nature. There's some 3D stuff, but in general, you're dealing with data, with 2D things. And also, the interactive surfaces are kind of mostly planar, kind of 2D in that sense as well. Same thing goes for the phone, where the actual screen is having a dual duty there. It serves both as an input and an output area. But again, flat, rectangular, digital space. In many ways, I find it not much different than, this image is 1963. Ivan Sutherland's sketchpad. In many ways, you have a flat rectangular screen, mostly 2D, and you have some keyboard and mouse, not mouse at that point, but you have some keyboard input. It actually has a pen input, which is maybe making a resurgence again, right? We might see a lot of that stuff. Definitely the Surface Pro device that I have has a stylus built in. But in many ways, the fundamental nature of the way that we most consume the information on our digital devices and the way that we most interact with them has not really changed that much. Touch, I think, is a big step, but it's just a step in that direction. I believe we're seeing the displays becoming much more diverse recently. There's now smaller, bigger, higher resolution, brighter, visible in sunlight, 3D, interactive, all that kind of stuff. But more interesting than all these commercial ones are some of these ones that are coming up, such as flexible, holographic. If you can guys check out, there's a couple companies right now. One of them is Zebra Imaging that they're showing pictures here, that are working on fully interactive holographic 3D displays, which are really hold huge potential, but they're just in an infancy. But it's really interesting, as well as ephemeral. These are really fun to think about. Fog screens, or this is a display where they turned basically a surface of a bubble. It's a colloidal display as an actual projection surface, as an actual interactive surface. It's really fun. They demoed it at SIGGRAPH a couple of years ago, 2012, right? But anyway, what all of that is kind of pointing in my mind is that I believe that we will be, if not, we're already kind of there, we will be able to basically transform any surface of any object into a display. Fundamentally, also, there's another trend that's helping this idea, and that is the rise of digital fabrication and the fact that we can manufacture things and encase them in a much more simple and automatic way. Together with this transition in the displays and being basically of a variety of shapes, I think all of a sudden we can start thinking about changing the nature of every single surface and making that a part of the interactive digital vocabulary. But fundamentally, interactions, I still think, are not keeping up. We live in very visually rich environments on the computer. But I like thinking about the interaction part still being stuck in primarily buttons, movement, some stuff with Kinect. Fundamentally, the way that the interactions work is they reduce the expressivity of your body into a very few variables, mostly on-off states, or even in the case of Kinect, the way that you really interact is they reduce the whole body into 23 points in space. So it's 23 points in space represent everything that they know about you, pretty much. It's a huge reduction of dimensionality. It allows for creating a content of it, but it loses the dexterity, it loses the expressiveness, it loses the analog feeling of a lot of these interactions. I love this picture because this is, I firmly believe this is still how the computer really sees us. There's one eye, most things are not stereo. There's 2 ears, you can kind of hear 2 sides stereo audio, and mostly you have a one big finger for tapping. You might argue at this point you have 2 if you want to pinch to zoom or do a couple things, but in general you're like a big finger with an eye. The way that I think that the way that we should think about this is really trying to look at interactions that are richer, that are higher bandwidth, and that are more analog in nature rather than the digital kind of. We're adapting well ourselves to the nature of how the computer would like the input to be rather than the way that we would like to interact with it. So I'll talk to you today about several different projects that kind of explore this space. And mostly, I know it's kind of tough because this slot is right after lunch, and mostly people just kind of want to fall asleep right after lunch. So most of these talks are going to be over videos, and hopefully they'll be engaging enough to get to see some of the fun stuff. Now, all of these projects actually have a unifying thread, and that is they're fundamentally a combination. They're enabled by a combination of a camera and a projector. In this case, a depth camera, a Kinect camera, and a projector, because basically that's an enablement technology here. And we use those, as I said, to kind of enable the interactivity on any surface or between any surface. So one way to think about this is to look at this as computational illumination. Rather than having lights the way that are really done right now, we are able to have smart lights that can both sense the activity of the user in front of them and actually direct and individually address different portions of the projection area with different colors. We're not the first ones to be doing this. I don't want to claim that this is an idea that kind of I invented. It's just an idea that I think is pretty powerful, and we've in contrast to some of this earlier work, which is super inspirational in kind of the I/O bulb or the Office of the Future or everywhere displays, what we managed to create is for the first time we have working depth sensing cameras. We have enough computational technology to actually start understanding and reasoning about the larger space. So we were for the first time able to actually create end-to-end systems that are not super dependent on predefined spaces, on predefined interfaces, and predefined kind of modeled environments, but really start to think about these as how do you embed them into a space and start reasoning about them at runtime. Yes?
Interesting that even in the Office of the Future, he switched over a laptop.
Right. Yeah.
Oh, he's talking about phone. Yeah.
As you know, this is an artistic sketch of the Office of the Future. They did a lot of work in that space, but they haven't really produced the Office of the Future in that time. It was just it was basically a little bit too far out given the computational capabilities of the time and where they were. But they definitely laid very foundational work in structured light and kind of sensing approaches there. Again, it's also one thing that's really fascinating to me is lately there've been this whole area of art called projection mapping. Of art is basically going and taking a very bright projector and doing really fun stuff on buildings or doing different illusion. And again, this is very related because basically they're augmenting the existing reality and turning it into some new, basically making new effects. But one thing that's very different from our work is that they completely have complete knowledge of what the actual environment is that they're augmenting. They're completely taking every single aspect of it, modeling it, and augmenting it in a kind of post way. So what you're seeing is basically an art production. It's not a real-time system. Also, there's comparable ways to think about this space in terms of virtual reality or augmented reality with glasses, and many ideas that I'll be talking about are actually completely relevant in that space. I'm not saying this is better. This is in many ways just different or complementary. I think one fundamental difference that you have between any kind of immersive VR space and what I'm talking about is that the systems that we've worked with are walk up and use. They don't require you to wear any extra gear most of the time. You're still allowed to basically reach for real objects. You live in reality. You're just surrounded with a little bit of enhanced reality rather than completely replacing what reality means, as is done in a kind of a VR headset way. All right, so now that this kind of sets the tone, I'll tell you a little bit about the first project in this space that we've done a couple years ago with a colleague of mine, Andy Wilson, up at Microsoft Research. And the main idea there is that we put a couple projectors and couple depth sensing cameras in the ceiling as a form kind of a chandelier right there that you see that right now on the screen. The cameras that we used, this was prior to actually releasing the Kinect. So these are PrimeSense cameras that came, there were prototypes that we used in the lab to enable us to aggregate all this information, all the 3D structure from the entire room, and map it out into one single unified space. So that we tile these projectors and cameras to basically increase coverage, not so much to have much overlap. And then when we combine them all, register them all into one single space, where fundamentally you could start thinking about designing interfaces, not in a typical way, like this pixel on screen relates to this particular object, but in kind of a mechanical way, like, oh, I want the menu to be a meter away from the table down on the floor. And that is really liberating. One thing that you can do is you can turn any surface into kind of a multi-touch surface. So here I'm showing you a standard desk or a wall. And again, what's interesting there is all of this is performed by literally processing depth data in space rather than having any kind of sensor augmentation of the surface itself. Because we know everything that happens between surfaces also, you can literally touch the wall and the table and make a conduit and transition objects directly that way. We also imbue objects, like if you take the picture and you want to hold it in your hand, we give it a little bit of physicality. So literally you can just walk it around. Now the system does not actually know anything about hands or objects. It just behaves in a kind of physically realistic way. So this ball just has a little bit of a physicality property, knows what gravity is, but doesn't want to make large jumps, which allows you to pick it up with any kind of object. It's not sensitive to having to know, is it your right hand, right wrist type of thing that picks it up or not. Another thing that you just saw was, you can touch different objects to move objects around, as well as this menu that's oriented in space. So literally, if you reach in into a particular area, you end up having a virtual menu that pops out, and you literally just trigger it that way. That's just kind of gives you a sample of how we do this stuff. Yeah.
If you don't mind me asking, just could you do like, because you have the 3D data of the hand, is that fine enough resolution that you could then warp the projection image so that rather than it looking like a flat projection on your hand, it just unwraps it?
So in this case we didn't. I'll show you the next project actually did exactly that. There's a couple of them that, so this is a couple years old at this point, but this is kind of the first thinking that we had in that space. And yeah, absolutely, you can absolutely do it. The menu right now didn't. The menu did one smart thing, and that is that if you have a unified way of thinking about space, some of the tricky things in collaborative interfaces, which is how do you orient something or what do you do, all of a sudden become trivial. Because if you reach into this virtual menu space and you want to project a label, you can very easily figure out connectivity and figure out where your head is, like what's the highest point of that thing, and orient the label directly towards you. So if I reach from here, the photo says, it's very readable. If I reach from here, the photo says it's readable from here. If you reach right in front of me, you get a different label. You get a label that's oriented to you. You kind of get that for free. You don't have to do any kind of extra sensing, extra combination, sensor fusion, or anything like that, because you can literally take all the data that is depth data that you acquire and start reasoning in a 3D space. This is another good example. Oh, I just messed it up. I don't know where we were. Here. Let's start from here. There was another, maybe. Here's dropping it onto tables. This connectivity, for example, if you take one side and put it to the other side, it really, we're not computing it, again, based on any particular skeletal data, but really on 3D connectivity in space. So literally, you can actually go and shake somebody's hand and move the object directly, kind of close the loop. And you'll see that in the next segment, I think.
Did you have to predefine what the projection surfaces were?
In this case, we did. So we had a little simple calibration procedure to make the table and the wall kind of a special surfaces there. Here's the idea of, you see Andy and me kind of go there, shake hands, and we can move the picture from the wall through us, through our apart. Now, what enabled us to do this is we took 3 images. This is the live feeds for cameras, but it would be really difficult to author these environments if you had to think about these camera views. So instead of thinking about all this stuff, we basically unified it in a one unified space, and you'll see that down below. So rather than thinking about 3 segmented and you know how does a particular icon move from camera A to camera B, once you have them unified and once you think about them as a 3D space, it ends up being much simpler to reason about that. We also do. So this is an example. This is kind of a debug view, but really what you're seeing is a depth sensing as well as the kind of interactivity with these physical objects. And here's kind of what happens with the menu. I mean, very straightforward, very simple by today's standards. Now, it's very noisy and all this stuff. It did improve with the actual Kinect, and eventually it's going to improve even more with the new version of Kinect. This is interesting because this is basically a reprojection of depth data from a perspective of a table. You can say, like, what does the depth data look in the segment of the table that is 10 centimeters above it? And what you end up is images that look very similar to what you would expect in any kind of a multi-touch device, right? They would give you this tracked components, and you can literally map them to a touch-based interface like that. It also gives you this ability to synthesize virtual cameras. You can create views that are kind of orthographic top-down views of, there's no camera that actually has this particular view, but this gives us a top-down view of the entire space, and now you can start reasoning about who is where and where are the users and all sorts of, who is moving an object from one image to another image. All right, so the next project in that space is basically dealing with some of the questions that came here in the audience, and that is one of the things that we wanted to do in light space. The interactions are very crude. Like, instead of even having a touch-based interactions, they were mostly based on blobs and kind of like, you can move a picture from here to there, but you can't really interact. You can't get to the dexterity that you would normally want, that you potentially have on your phone. So we created this project with an intern of ours, Chris Harrison from CMU. He's now a professor at CMU. He worked with us over the summer to make to use a depth camera and a projector and create interfaces on any particular surface, but they can be closely approximating the precision that you have right now on a regular touchscreen. So here's the idea that you're actually the interfaces map to a particular surface, whatever surface you end up having, and not only can track a point in space. This is a touch in space, but you also get it on very deformable surface. Your hand is a pretty non-uniform thing, and also gives you a good hover space. So not only do you know when the finger is touching, but you actually know when things are above. This is a depth view from above the the view from our camera. And you see the classification of fingers. The way this is implemented is a particular piece of hardware at the time, which was a custom-made depth sensing camera that's a short-range one. It works from about 10 centimeters to about a meter, combined with a little pico projector. But what it enables you is to literally walk up to any particular surface and tap on it, and all of a sudden the information just appears there, right? So if you just have a notification, you can just pull up the thing, and now maybe you want to find some little bit larger surface, like you walk up to the wall, and now just drag out the interface where you would like to read out that particular email, and maybe you pull up your hand again there, and now I'm not saying that dialing phone numbers is actually really interesting. In many ways, I think it's kind of an outdated idea. But what's interesting about that is that the precision of our sensor is actually good enough to tap these small, tiny buttons. We found that it's actually close enough to the precision of the regular touchscreen on the phone. Here's an idea of doing the same thing on kind of having a scrolling menu on your hand, and literally in this case, the reason why this works is because we have a very good assumption of where the camera is looking from. Everything comes from your body, so you can make easy assumptions about where the hands come in and how your fingers look from that particular perspective. So this gives you a feeling of how accurate our system is, how responsive. So you can do all sorts of annotations, and things are a little flowy. But again, these are just little prototype demos. What's really interesting here is there's a kind of a metaphysical question here is what is the surface that you're interacting with and what is the surface that you're interacting on? In other words, what's touching what? Because in many ways, these things are in contact. So one thing that we ended up doing is that we literally label everything that happens to be in front of you with a little tiny blue dot. So if you walk up to something, all of a sudden you see a couple blue dots on candidate surfaces. And at that point, whichever one you end up touching ends up being the kind of originating one, the first one that you start from. All right, so we looked at these interfaces from kind of a touch perspective, like how do you actually enable interactivity on a random deformable surface. And now we started looking at how would you actually present some three-dimensional data? How would you get content that moves up away from the surface and still give you this direct, uninstrumented way of interacting with it? So the next project is called Mirage Table, and that was done, again, following the OmniTouch work. And in this case, we have a 3D stereoscopic projector in the ceiling, and we have a Kinect camera looking directly at you here. What the system is doing is, in this case, is literally acting as a 3D mirror. So it digitizes everything that happens to be in front of the table and on the table, and literally makes a 3D model at runtime of that particular object. Now, that's cool, but all of a sudden, because you're digitizing everything that what happens on the table, including your hands, you can start running a physical simulation with that data. So literally, we're representing here our hand as a bunch of proxy particles, because if you run a physical simulation, it's good to have a finite volume and finite mass. If you have a deformable mesh, that kind of ruins the physics. So, but you can do things like this, where you can literally start playing with virtual projections in 3D, in mid-space, with your free hands. Because again, this system is digitizing and meshing up the entire 3D geometry of the scene in front of the table at runtime. It also is doing this perspective projection so that objects look correct from your hand. You see that you're holding this ball, but really the ball is projected over multiple surfaces for your eyes to be doing the same thing. Another personal favorite here is then all of a sudden, since you can do this digitization, you can start creating these interfaces where you have one Lego block and you can build whole castles of interesting things and concepts because literally you're just scanning, building, moving, and playing a little bit of a kind of CAD work there. So it's quite fun to do this. This all comes together in a game like this, where you literally bring in a bowling pin, scan it, and then now you can use a virtual ball. As soon as you scan that bowling pin in there, you can use the virtual ball to start bowling with it and knock it down and hopefully compete against it, right? So the time from the object being physical to the object being virtual but having physical behaviors is literally shrunk down to an instant. We just, it's a click of a button, or, happens all the time. We also hooked up two of these together, so you can literally have a face-to-face conversation. Almost think about it as 3D Skype. Not only that you're seeing somebody, but you can actually do things together. You have the same physical units. You can literally shake hands with somebody in midair. You have no negotiation time because you're seeing this in 3D. You're holding glasses, and you don't feel it. You don't actually have a haptic sensation there. That's something that's really hard, and we keep working on it, but we're not quite there, and I don't think we will be for a long time. But in terms of knowing exactly where things are and how do you put this stuff together, you literally have a shared interactive space with zero negotiation, or all the same negotiations that you have in physicality, as if you were sitting and talking to somebody across the table. Yeah.
So that bowling experiment, how did you create a mass model for copying physical to virtual?
So there's a couple things that we assume there. It makes a couple assumptions to make this possible. One is that we don't really scan things from multiple sides, so we really only see one side of an object. So when you scan a bowling pin, you get a front side. We just rotate that and make an assumption that the object is symmetrical, and fill the bottom. So once you do that, we assign a simple mass to it that's proportional to its volume. Assume basically uniform density of all different objects. But we have looked at different classification of objects. So looking at, can you find and can you index into something like that? This is a Duplo block and this is a bowling pin or something like that. So can you look up the mass rather than infer it? But right now in these demos, it's basically the mass is proportional to the overall volume. And then that's also a problem for simulating physics with your own hand, right? Because if you're only seeing the top of your hand, you could potentially have infinite mass. This can go, like the depth can go into infinity. So instead of doing that, we literally represent. It's a packing problem. We pack it with proxy particles, each little spheres that represent, basically fill up the contour of your body, and those spheres. End up being the interacting part. So they get updated through optical flow and through the basically the depth information. So they get updated frame to frame, and they end up impacting, and they end up being the interactors in the physics scene. All right, I'm going to skip all the experiments. You can look at that in the paper. Another interesting one after we did all of these ones is, how do you really, can you have a movable kind of projector camera system to allow you to really encompass the whole room? Like if we wanted to turn this whole room into kind of augmented reality through projection system, can we have a pan tilt unit that would allow us to do that? So we built a machine called BemaTron. We try hard on our names to just make sure that they're as good as you can get them to be. And the BemaTron looks around, and it's again a Kinect camera and a projector, 3D projector, and now it tracks a user in space and can project onto their hands. It can project different things, and I'll show you a couple different things. One is also you can run this like little car simulation and all over different geometry in there. It doesn't actually care what the geometry is in the scene because it looks at, this is the depth mesh directly. And when it finds people, it turns on the skeletal tracking. So here you'll see us doing a little dance just to verify that it works. It's always important to dance in your videos because that, shows that it's not fake. We also, an interesting challenge in all of this stuff is that, I'm going to stop this for a second. An interesting challenge in all this is that if you have a steerable display that looks around, that means that at any given time, it's only going to see a certain small portion of the entire space. So if you're relying only on vision to interact with it, you're basically continuously chasing it around to try to be in its view. So what we did is we used the feature of Kinect that's not often used in kind of these hacky Kinect demos, which is the steerable array microphone. So very quickly, by just placing 3 of them in the corners of a room, 2 of them kind of parallel, 1 vertical, you can basically triangulate the person's position. With very little calibration, we get down to about 1/2 meter accuracy of localization. So literally what we do is, I'll show you, we literally are able to call up. So there's 3 Kinects here. We don't use their actual depth cameras. We just use their array microphone. And you see the localization here. We also put in the voice of GLaDOS from Portal, so it has a little bit of an attitude.
BemaTron.
I was just talking to Wendy this morning, and it was quite amazing. Let me just pause this again. It was quite amazing. That's the only kind of anthropomorphic thing that we added to BemaTron. It basically responds to when it turns. It just says, "Yeah, what?" But it's amazing how much difference that actually made, and a lot of people coming in there and literally just engaging with it. There's nothing else the BemaTron can say. That's it. I mean, "Yeah, what?" is pretty much the extent of its vocabulary. But even just that much, with the physicality of turning towards you and shining up and kind of looking at you, is enough completely to think about it as almost a real thing versus a device in the ceiling. So that's just an interesting tidbit there. But again, really what BemaTron shines at is this idea that all of a sudden it can project an object, it can respond, that object can behave in a physically realistic way. So in this case, we're driving an RC car, but the RC car is virtual completely. We're driving it with a physical steering wheel. So that's a Kinect steering wheel. The car is projected. not the greatest shot, but this is good. Now, if you had to pre-calibrate for this, this is fine. But this is all done at runtime. We can literally move this ramp, you know. And if you drive the car slower, the car is going to just flip over, right? It responds in the same way that the real car would, right? If you kick it, it should flip around. Even though it's projected, it has a complete physical reality that's believable in there. We also correct for view, right? So I told you with audio we track where you are in the room, and we just give you the correct perspective view. We can also run the car in stereo if you want to see it in 3D, but in general we find it more interesting to just drive it in 2D. The way that it works is we use Kinect Fusion to literally make the model of the environment, but not also to make the model, but to smooth the model. Because think about it, every single little bump on the floor, if you have to drive a little RC car over it, ends up being quite a disturbing thing. So here you see how it updates over time, right? Literally, you can make a new model and ride over something. And that's exactly what we do. We just literally move things around the lab and drive over it. You can think about driving it over your car. You can think about all sorts of different things in there to engage there. This is a little homage to an old demo in computer science called Put That There, where we literally, what we're doing is we're scanning people, we're making sure that their skeletal tracking work, and then we give them a little speech interface that they can move things around and say, you know, I want something over there, I want it over here, I want to kind of look at some slides, etc. So I'll show you, you'll see in the next slide how that, in the next clip, how that works.
Put that there.
Now, there is no unified model of the room in this case. It just looks for, extends the trajectory of your hand and looks for the first available surface where it could be basically intersecting. So you can keep it there, and now she's going to put it somewhere else. I don't know, on the floor, I think.
Put that there.
Again, these are goofy examples. I'm not saying this is the best PowerPoint tool ever, but the power of and combinations that you have when you combine speech, tracking, and understanding of what the geometry of what the room looks like is quite mesmerizing. You all of a sudden can do all sorts of funky stuff like that. All right, so this also brings me to another project that's very recent. We did this just last year, and it's called illumiroom. You might have seen this, but I'll show you just the preview video just to kind of get us started. Maybe we can dim the lights a little bit.
Xbox, go big.
Now, this is what a typical research video should look like. You know, if only you had a budget of, you know, what exceeds a lot of people's salary. Anyway, the interesting thing, this was shown at CES at the beginning of this year, and they wanted to have a really splashy demo. But the honest truth about this is, yes, it's a fancy production, but none of it is fake. They just literally shot this in our lab with an actor, or actually two actors, a lady and a guy, and they shot all the stuff is basically real. They just shot it with a very nice camera and a very nice setup.
I was actually I was one of the participants for that, so I can vouch for it.
Why aren't you on the video?
I know. I should.
There were lots of volunteers who wanted to be in the video, but you know they had to pick talent to appear, right? So. That was one of the artistic freedoms that allowed them to have, right? Like you pick whoever you want, it's fine. Anyway, so all jokes aside, the illumiroom system is basically the same components as that all the systems that I talked to you so far, and you can see the trend here. But the idea in this particular project, and by the way, I have to say this is a project mostly done by an intern of ours, Brett Jones from University of Illinois in Urbana-Champaign. Brett and I and other folks have worked on this project to try to look at how do you extend the experience of watching television or playing games on TV right now into your real living room without necessarily moving you out of it, without changing physically how your room looks like, or without actually knowing what your room looks like either, right? So some of the same problems that we had in before, in BemaTron and Mirage Table, all that stuff, they're all coming back again. In illumiroom, we made a conscious design decision to not change the content on the television. In other words, if you don't have illumiroom, you get the same feed as everybody else on the TV. So we don't change. In no way are we ever changing what's actually shown on the screen. What we are trying to do is we are trying to give you visuals that are in the periphery that complement the content, and that also in some cases respond to how your room looks like and what your room does. So the vision that we had, kind of the way that we started, is what if you had this little ProCam system, projector camera system, that you plop down on your coffee table, and it automatically finds your TV, and it just presents you with this extra view. We ended up not putting it on a coffee table, we put it on a bookshelf behind it, but kind of a similar content. We did end up realize automatic calibration, so the system is literally self-calibrating. You put it down, it splashes some things on the TV, it finds exactly where the TV is, it splashes some structured light patterns on the surround, and gives you the, it finds its projectable area, and at that point on, the system is completely kind of self-driven. It just gets the feed out and projects it outside. What's up?
Who's running the TV?
It's a good question. So currently, both of them are run from the same PC. So there's one computer where we literally play a game. We set the main display to be the TV. We play the game, in this case, Red Eclipse or something else in there. And then we do a couple ways of getting the content out. And I'll talk about all those ways a little bit later on. But currently, it's all the same system. It is also foreseeable, there's lots of move in the industry to have attached screens. Like Xbox, for example, have a smart glass appliance, which is basically, you can run it on your phone, you can run it on a tablet, you can run it on whatever, and it can get direct video feeds from the Xbox to give you accompanying content. In many ways, you can think about illumiroom being a smart glass appliance for Xbox there's just not a display of this kind, it's a display of projector kind, right, that augments your additional display. So I want to talk a little bit about kind of some of the smarts that we do. We compensate in illumiroom both for your geometry of your room, but we also compensate for appearance of your room. So in other words, your room is not just white furniture on white background on white carpet, all same BRDF, all same reflectance properties of your furniture. What it does not compensate for is situations like this where, if you do decide to put your TV right in front of the window with some glass stuff in there, it's going to be really hard to do illumiroom setup in this particular case. There's no way for me to compensate for, going across the street, sunlight, and all that kind of stuff. But in general, for most people's setups, you do end up having compensation. What you see here is, this is what our projector is actually projecting. This is what the image looks like in the scene. So in the scene, we specifically had some white and black boxes from IKEA to kind of not try to cheat too much. And you see how we compensate for them. You can't completely overpower the nature, but you can get very close. So the preview video gave you a whole bunch of illusions all at once, kind of give you as much shock and awe as you can take. I'll guide you briefly through all the different design explorations that we did, because we started basically with this particular one, which is basically you steal a texture from the game, and then you see it projected on the periphery. So this game is called Red Eclipse, and we're just literally playing it, and all of the functionality of illumiroom in this setup is just focus plus context, right? It gives you a wider screen. Honestly speaking, if that's all you want to do, I would highly advise you guys to go and buy a bigger TV. Because I think in some ways it's missing the point, and that's what we realized early on. Even though it's impressive for a very short time, and it's not really using it to the full extent. What's up?
How does that work with racing games? Are the cars on the outside or in the main TV?
I have an example of racing games, so you can tell me later on how it works. But I think, yes, the idea of where your avatar is, right, whether the avatar is car or your hand holding a gun or something like that, is an interesting one, right? It might be too far away and you're not rendering, all sorts of stuff. I don't, in reality, I don't actually find, we showed this to many people. Many people have played it. We showed it at SIGGRAPH this summer, and nobody really complains about it not being exactly right. So I don't think it actually would be that much of a problem, but we have a couple ideas about how to fix it, how to make it more right. However, we haven't tried, as I said, we keep the on-screen content, we haven't changed it whatsoever. So all we do is change what happens outside of a TV right now. So so one of the things that you can start, when thinking about these illusions and this design space of what happens around it, you can start thinking about what your eye actually sees, right? So we started with that. We looked at, oh, in periphery of your retina, you're much more sensitive to contrast and edges and contours and not really to textures and color, right? So your eye doesn't really even perceive that. So if you lose all the color and just highlight the edges, you end up having a much more immersive, there's much more peripheral motion happening in your retina. You feel much more drawn into it, even though you lose a lot of higher frequency details. Now, of course, that only works if you're actually there and focusing on the focus, right? If your eye starts wandering around and looking for extra content, then yes, you're kind of missing some stuff around. But in these cases, it's you're playing a game. You don't want to get shot. Like this is what you're trying to do. You're focused on the screen. Also, when working with game designers, we had a bunch of kind of critique sessions in there. And one of the suggestions that very early came on is like, you don't want to bleed out everything. Maybe you just want to be selective about only the content that really matters. So in this case, the explosions, the enemies, the weapons that you need to pick up, bullet shells, things like that bleed out of TV. But everything else ends up staying within the TV. And I think that's particularly powerful, right? It kind of gives you this extra sense of like, the enemy's coming, or I forgot this, there's a grenade back there. But other than that, you don't necessarily have to go and be overloaded with all this extra information. We also, this is just this kind of highlight, we can basically segment your furniture, segment the experience however we want to. We can find, for example, where the back wall is automatically, because we can just find the largest vertical surface, for example, in this case, and then make it appear like your game is being played on the back wall. The back wall is the portal to this other world. Your furniture is not. And this brings us to this idea that your furniture can somehow be included in the game. So one of the things that fascinated us for a long time is that games and TV shows and pretty much all the content that you see on the television has a distinct visual language. In games, that's most apparent by looking at the shaders that they apply and the rendering of that particular game. If any of you have ever played the game called Borderlands, you have this really highly outlined view, and that is kind of the signature view of that particular game. Now think about it, you can take that same shader and apply it to reality. You can take the shader and make your room look cartoonish or outline, make it look black and white if you're watching film noir, or having kind of different style of the appearance of your room can match the on-screen content. Which is really fun, because all of a sudden your room responds correctly. And now you can also start really messing with people. You can start having these visual illusions where things are very trippy without necessarily requiring any drugs. All I'm doing is just reprojecting. All I'm doing is just reprojecting a little bit of a texture with some distortions there. Those are particularly effective. Actually, we have the same way to trigger these illusions on, let's say, a fully blown focus and context setup, right? And they're nowhere nearly as interesting because that's a virtual world. You don't really care so much what happens there. What's effective in these cases is in this ripple example, is that you know that your furniture should not be moving. Your brain is very sure of that. Otherwise, things are not right? It's something is happening. So when they do visually move and your brain is still focused on the screen, you don't really see the discrepancies that much between the projected and the real. It ends up being quite a powerful illusion. We've played with lots of other ones when you think tilts, when you're making corners and all sorts of fun stuff. And all of them are really, really powerful, especially if you're focused on the game, right? Because you just perceptually, that stuff should be very solid. This should not be moving, and it ends up messing you up. Another ones are completely virtual kind of effects, like you can have a holodeck illusion, right? And again, these are just blue lines projected on the background, nothing fancy about that. But if they're tightly matched in motion to whatever happens on the screen, they're powerful. Here's a star field. Think about having a star game where all you're doing this. We actually put this in conjunction with a program called Worldwide Telescope, where you're exploring stars. And even though the white dots are completely randomly generated white dots that are just there, the immersion level is amazing. All of a sudden you feel like in this, you're in this planetarium experience, even though it's just your living room. This is a car game that you kind of asked about. In this case, we only stole the lighting from a game. So the lighting and the shadows is completely synthetic, but the furniture is real. So just imagine you're driving through a tunnel, you're driving through some overhead lights. Literally all the shadows are simulated from the geometry that we have. Everything is kind of simulated at runtime, but it corresponds, again, accordingly to there. And you kind of see the extra car there. The discussion always, some people think the shadows should follow the car, and some people think the shadows should follow where you are, 5 meters behind the car, and that actually ends up affecting the lighting. So that's kind of open to the debate. But I think that those are some of the game design choices, not necessarily technology choices. You can render them whatever you want to. Here's an interesting one where the illusion is completely artificial. It's snow illusion. It's, again, white balls falling down. But when tightly matched to the content of the game, it's quite powerful. So in this case, we have a car racer game. Notice the snowflakes cannot actually go through your wall or your furniture. They kind of end up accumulating back. Now, if you start driving forward, they start rolling towards you. Also, the longer you drive this game, the more white you can make the horizontal surfaces. The snow accumulates, all sorts of goofy things like that. And before you know it, you have little kids riding through it and trying to pick up snowflakes and not really paying attention to the game, which is exactly what you want to do with these systems. That actually kind of means the system is working. You're having a lot of fun. Lastly, I think I'll show you this one, which is the idea that the content can literally escape the TV. And we use the same content and the same physics. This is just a canned example, but you have a grenade falling out, maybe hits your bookshelf, hits your floor, rolls underneath your coffee table. Now you might want to pick it up and throw it back in the game before it blows up. Or you might want to wait and see how your furniture shakes, right? Either way, it's fine. All right, so let's talk about something that Michael brought up before, which is how do you actually drive these illusions? How do you get to the content? How do you get to the motion and all that stuff? And we, in this paper, by the way, all of these are papers, right? You can always look up more stuff online about this. But in this one, we explored 3 fundamentally different ways. One is, ideally, you're working with the game. Ideally, you have source code access, and you're working with the game. And in that case, it's actually not that difficult to make the game double render, right? Or render certain things. And all you do is you have the same rendering logic as you already have in the game. All you're doing the second one where you set up a camera with a wider field of view and make the same rendering out there. Or you cull certain things out of that rendering if you want some selective parts. Now, but that does require you to hack the game, basically, which is what we did with a couple of these games. We also drive a lot of these illusions completely synthetically from the vision of what happens to happen on the screen. So here's the game on the side, and we run optical flow on it, and then we drive the kind of holodeck illusions or the star field illusions or snow illusions based on that kind of a motion in the scene. We also can intercept your controls. A lot of controls are very kind of straightforward to take. Like you just hack the controller, get the controls and map them directly to that, to your experience. In a little UI, you kind of connect the inputs to the outputs. And you can actually think about that as being kind of pre-scripted. You get that with the game for the games that don't necessarily allow you to scrape their content out. So there's multiple ways of triggering this stuff. And we also looked at, beyond gaming, we looked at the different ways that you can set up illumiroom setups for other kinds of content. So we created little vignette videos that look at sports and fashion and all sorts of kind of music video type things. And here's like just a little bit. This is, for those who know, this is Eric Horvitz's hockey game. Or a bike ride there, or have a fashion show where you kind of have a lot of trippy visuals on the side. And it becomes really interesting when you have different content. The content that doesn't exactly match is not just an extension of content, but content that just draws your eyes to it, or something happens, right? We would love to have the ideas of, you're watching an NFL game and a quarterback throws the throw. the focus really focuses and pans around and is there, but you're also seeing the fans and the cheerleaders and the opposing fans booing and all that kind of stuff in the periphery, and it becomes a much more interesting experience. So the way that I started thinking about this space recently is kind of in this big closed loop where you have with Kinect enabled, and arguably it is really a revolutionary product because it took technology that was really difficult to obtain and expensive and kind of lab driven to kind of masses. But Kinect literally allowed you to transport yourself into the game. All of a sudden, you can become an avatar. You can impact the game. Your motions, your dances, your whatever kind of movements can become part of the game experience. What illumiroom is trying to do, and what some of these projects that I talked to you about today are trying to do, is literally do the opposite. Complete the loop. So they take the game experiences and adapt it to your space. Make that more relevant to where you live and how you live, so that you can literally not just always have to teleport yourself into a different world. The game can come back there, and the game can be adaptive to the to your particular environment. It also means that if you change your environment, the game should adapt there. But that is kind of that's the bonus in many cases. It's a difficult case, but it's a lot of fun because you don't have to play the same experience all the time. So again, all of these experiences were enabled with a depth sensing camera, Kinect in this case, or a precursor to Kinect or whatever, and a projector. But I do want to stress that the ideas are, in many ways, transcend this idea of projection-based augmented reality. They're not just spatial augmented reality. They are also augmented reality in a general case. A lot of them can be applied to head-worn displays or other forms of augmentations. So I will leave you with this idea that we will be able to transform, I firmly believe that, pretty much anything around us into kind of an interactive display. Just the challenge is like, how do you actually interact with it once it's everywhere, once every single pixel is addressable and there. This does not mean that we're going to, I'm not arguing that the existing input devices or existing displays are going away. I think there's lots of uses for the phone. As I told you in the beginning, I actually worked on mice and keyboards. I don't think they're going away either. I think it's really about extending what our interaction vocabulary is, extending the bandwidth of options and how we interact with computers. It's not so much about we're going to be replacing the existing devices. I think we're just going to complement them and extend them in interesting ways. So I want to thank my collaborators. There's a bunch of folks who are just fantastic to work with. And at this point, I'll just take some of your questions. Thank you.
Yeah. So in a lot of the nice examples you were showing of tracking people and the like, there's still like a little bit of a latency, like in the system.
A lot of latency, yes.
Like, what's the biggest challenge? What was your biggest challenge to get it to the low latency already have it, and what would it take to push that?
That's a great question. So there's a couple answers that we have about this. Latency is a big killer in all of these systems. End-to-end latency in most of these projection systems are on the order of 100 milliseconds. That is, if you don't introduce even the slightest bit of computation. What you're really doing is camera is capturing, you transfer it over USB, you get there, you display that same image back out to the projector, and the end-to-end latency in there is about 100 milliseconds. That is enough that if you have a moving object, if you move your hand at a meter a second, you're like, the thing is off your hand. So it's a big problem. I think fundamentally it's a problem that most people in the industry are well aware of, and there's lots of work recently that is there. There's also a really interesting paper by Albert Ung and Paul Dietz about measuring latency and having going down. They found out that people are, contrary to popular belief, we can really easily detect latency down to even 1 millisecond. But what's really more interesting about that particular work to me is that the way that the low latency systems, the way that they make you feel, this is a fundamental shift. Once you get down sub 10 milliseconds, so for the people who don't know about that system, it was basically an inking system where you move your finger down and it just ends up drawing ink behind it, and they introduce varying different latencies to give you a perception of how it feels with latency in there. So once you get down to like 5 milliseconds and 1 millisecond, you fundamentally go from believing that this is a device that renders your stroke to believing that there's paint coming out of your finger. literally kind of feels like that. It's fundamentally different, and it's hard to display. It's hard to describe, but that's kind of what it is. I think that's really interesting. Speaking in our systems, what we try to do, we of course try to optimize our code and things like that, but there's not much what we can do with commercial level kind of Kinect sensor right now, or with commercial level projectors with mostly buffer, at least one frame, if not more, to do this. But I think we had several projects, some of them we've done this summer as well, hopefully they'll appear at some of the conferences, where we looked at different approaches for predicting motion, because a lot of these motions are actually very predictable. If the ball is in midair, you're only governed by laws of gravity. You can completely extrapolate their positions and correct for projections to do that. If the motions of the hands are, there, you can use kinematics and kind of try to maybe look up previous likely positions and what the next likely positions in your next couple of frames are in there. So I think there's approaches to combat latency, even kind of purely on the software side, that really haven't been played out yet. We started to scratch the surface there, but ultimately I think it requires kind of everything to come together. I think it's one of those brute force approaches that you need to optimize every single part to get it down to 15 milliseconds or less.
Horrendous.
Yes, it's very problematic. The nice thing about some of these systems, though, is so, for example, illumiroom or the BemaTron, things like that, unless you're projecting on humans or highly moving objects, most of the room, for the most part, is actually very static. So there, you kind of control all the aspects of it. And that's actually, when people ask me kind of compare and contrast type of head-worn displays and projection-based displays, that's actually one of the big benefits of these projection displays, is that our immersive setups, our augmentations are rock solid on the static geometry, on the geometry of the room. On a head-worn system, unless you get latency down to like really low levels, like sub 5 milliseconds things, you're always going to notice this jitter and lag, and things are never quite aligned. Things are not rock solid. The way that these illusions, like the way that the wobble illusion and all that stuff works, is because it's pixel rock solid on the thing, and when it starts shaking and moving, all of a sudden you realize, holy crap, this is not the real anymore. I mean, this is not how it's supposed to be. If it was wobbly all the time, doing this illusion, it just doesn't work. It's just like, yes, you can run the same shader code on that, but it's just nowhere nearly as effective. Yeah? Any more questions? Oh, sorry.
Are you working with the military on any of the systems for pilots?
You mean like heads-up displays?
Well, beyond heads-up displays, like the helmet display.
Like the F-35?
Yes,
yeah.
yes.
I am not right now. At Microsoft Research, we don't engage much with DoD and things like that. My primary, when I was doing a PhD, I worked with Steve Feiner at Columbia. We worked with a lot with Office of Naval Research and lots of heads-up displays there. Also tank turrets for tank commanders, things like that. And again, I think those are very complementary, interesting challenges. But at this point, we haven't worked with the DoD on anything like that. I'm well familiar with the field, but I'm not involved.
Well, maybe they may have approached you.
Well, we definitely spoke with. I mean, I keep in touch with a lot of those folks still, but we're mostly focused on consumer kind of lightweight gaming, productivity applications, things like that. Things that are kind of off focus for Microsoft right now.
Those seem to be merging.
A little bit. I've heard there's also lots of problems with F-35 helmets and things like that. So and a lot of them have to deal with this lag and field of view and just complexity and reliability of these systems over a long time. I think those are really challenging. Some really good challenges. Yes, what's up?
More of a speculative question. Looking at all of the challenges that you face with this kind of work, if you could suspend one law of physics, essentially, if you could just magically solve one of the problems you have to deal with, whether it be sort of how brightly you can project light out into the world so that you can get outside of caves and these kinds of things, what is it that you would really want to fix or to change that would enable that next layer of interaction?
That's a very good question. I mean, I think there's a lot of them. Brightness is definitely something that is really interesting to us. So I really like laser projectors for a couple particular reasons. One is that they don't require focus, and that you can basically shine them out and images in focus from here to infinity, right? If they're really collimated laser projectors. However, I look at the trend of the increasing brightness for some of these projectors, and granted, they're working on limited power budgets. In terms of they all are trying to focus to be a laser projector for the phone, all the companies and things like that. But still, like the trajectory of increasing lumens output of these projectors is very slow, and to overpower this for the longer term is not the case. But the bright projectors are all basically little fridges, right? They're kind of they require a lot of stuff, and primarily it's the heating and the light source, and kind of how do you get all that stuff out of there. Solving that would be really kind of instrumental in that case, because it would enable you to shrink things down. Right now, there's this kind of low power, low lumens, small package thing, and high power, high lumens thing. And a lot of the really interesting application would be if you had a basically high lumens but small package setups.
So at which point this could stop being part of the room and start being part of
Right. Yeah. I mean, we're getting to the point where depth cameras. I mean, most people think depth camera Kinect, but the reason why Kinect is so wide is there's two reasons. One is it has this steerable array microphone that kind of has 4 different points. So there's a distance between each of these microphones, and also there's a distance between the two. The projector and the camera, there's about 10 centimeters of that, so it ends up being a bar. But right now, with the time-of-flight cameras, and especially ones that are on the market, or they're prototype stage, like the PMD ones, or Soft Kinetic, or Kinest, ones that are built into the new Kinect, those are all, fundamentally, they can be rather small. I mean, there are devices right now that are about 1 centimeter, 2 centimeters small. So the sensing part of this whole equation is actually getting miniaturized. The projector part is not quite there.
Great, let's thank our speaker. Thanks,
Thanks, guys.